Hello class, this is lesson 4.6. Here we look at inequalities dealing with polynomials and rationals. So we'll begin with polynomials, and here I did some rough sketches of what polynomials can look like. And when the outputs are positive, I wrote the graph in green. When the outputs are negative, they are in red. So as you can see by looking at these graphs, a critical point in the graph is when we cross the x-axis, because that's when it changes from negative to positive or positive to negative. Or the other case is we could bounce off the x-axis and it remains positive or the outputs remain negative. But nevertheless, whenever the graph touches the x-axis, something critical is going on. Either it's switching from positive to negative, or we might have a minimum or maximum, something. So it should make sense that when we're dealing with inequalities, what we first want to find are these key points here when the function equals 0. So I could start with a really easy inequality here. Let's say we have x squared minus 1, and we want to find when the outputs of that are greater than or equal to 0. Well, if you're comfortable with graphing, that is the easiest and most intuitive way to do this. So, you could start with the graph of x squared and then shift it down 1. However you want to graph it, you'd end up with a graph like this, right? And when it crosses the x-axis, that would be at either 1 or at negative 1. So these are the key points here. And as you can see, the outputs are positive here, where I will put them in green, positive here. But for these red outputs, the value is negative. And we were interested in when the output of the entire thing was greater than or equal to 0. And as you can see from this graph, that's when you plug in either negative infinity, open parenthesis, negative infinity to negative 1, or plug in numbers from 1 to infinity. That is, if we plug in numbers from here to here, or plug in numbers from here to off to infinity, the corresponding output will be on the positive portion of the y-axis. And I did square brackets here because it was less than or equal to 0. Okay, so if you do know how to graph it, then it's pretty easy, but let's pretend you did not know how to graph this. If you did not know how to graph this, how do we solve it? Well, step 1 is we find the critical points when the whole thing would equal 0. So then you solve this, and you get plus or minus 1, and then you could make a number line. So here's the negative 1, here's the positive 1. And what you could do now is just plug in some points in these 3 intervals. So we cut up the number line into 3 pieces, and we could plug in values back into the original function. So say we plug in the number negative 2 into the original problem. So we get negative 2 squared minus 1, 3 is positive. And therefore we know anything we plug in here will give us a positive result. Because back to sort of the concept here, if we plot whenever it equals 0, all you have to do is test a number between there, and it's either going to be positive or negative in these intervals in between the critical 0 points, because the only time you can change from positive to negative is if you first cross the x-axis. But if we plot all the points where it crosses the x-axis, then in the intervals in between are either positive or negative everywhere. Okay, if we plug in a point here, say we plug in the point 0, that's 0 squared minus 1, that's negative. So everything in here is negative. Then if we test a point here, say the number positive 2, you get 3 again, it's positive, everything in there is positive. and we get the same answer. Any number we plug in from -infinity to -1, or from 1 to infinity, will give this inequality. We'll make that inequality true. Okay, so again, we can look at some more polynomial examples. Oops. Okay, let's do a quadratic one. Okay, let's solve this one. What is 3x squared minus x less than or equal to 0? Well, first, step one is we want to solve when it will equal 0, because that will give us the key points when we cross the x-axis. And we could factor an x out of this, leaving us with 3x minus 1. So this tells us either x equals 0 or 3x minus 1 equals 0. So that is x is either 0 or x is 1/3. Okay, so we could plot those points. This is when x is 0, this is when x is 1/3. And yeah, we could just plug in some values. So let's plug in the value -1 to the original problem. That's 3 times -1 squared minus -1. 3 plus 1, positive, right? Cool, so anything in here is positive. Let's plug in a number here. Plug in what? So that was 1/3. What should we do? 1/4. If we plug in 1/4, do 3, 1/4 squared minus 1/4. So that's 3 over 16 minus 1/4. Get a common denominator, and this becomes 3 minus 4 over 16. So -1 over 16, and that is negative. So we are negative in here. Okay, one more part of the x-axis to test. Let's plug in the number 2. So it doesn't matter what number as long as it's on this piece. If you plug in 2, we get 3 times 2 squared minus 2. Okay, so that's positive. So that's 10 positive. Okay, now back to the original problem. We wanted this whole thing to be less than or equal to 0, or we wanted the x values that gave us a negative. So this time our solution would be 0 to 1/3. That is, if we plug in numbers here, we get a negative result, and that's what we wanted. We wanted to find the x's such that when we plug into here, we get less than or equal to 0. Okay, so don't make the common mistake that positive is always the solution. And even though I did positive in green, it kind of tricks our brain to think, oh, it's good and this is bad. But sometimes the answer is the negative intervals. You just got to pay attention to which symbol is being used in the problem. Okay. So let's move on now to some rational inequalities. And these ones are a little more difficult because we have not yet done too much graphing with rational equations, but that's okay. We could still do a similar test. So say, I don't know, we have 2x minus 1 for x plus 3. We want to find when is that greater than or equal to 1. Well, with a rational or with a polynomial, we always want 0 on one side. So first step is to get 0 on one side of the inequality, like this. And if it's a rational, we need a common denominator now. So now I'm going to have to rewrite the problem as 2x minus 1 over x plus 3 minus x plus 3 over x plus 3 greater than or equal to 0. So I wrote this instead of 1, but they're the same thing. This divided by that, since they have a same thing on top as bottom, it simplifies to 1. But now I have the common denominator. So simplifying the left-hand side, we have 2x minus 1 minus x plus 3 all over x plus 3 greater than or equal to 0. So 2x minus 1 minus x minus 3 for x plus 3 greater than or equal to 0. Okay, so 2x minus 1x, that just gives us x, negative 1 minus 3, negative 4, x plus 3. Okay, so now that everything looks clean, we could now make a number line, plug in some values, test when this left-hand side is greater than or equal to 0. Alright, so when will this equal 0? Well, for step 1, we want to find when does this equal 0, so we know what numbers to test. Right, and this clearly equals 0 when we plug in a 4, right? Plug in a 4, it equals 0. All the bottom tells us is the domain, so we can plug in a 4, and that's fine. The domain is that we cannot plug in a negative 3. But we know on the number line we should test the numbers 4, and this number is also important, so I'm going to put that on our test as well. Okay, so now we broke the number line up into 3 pieces. So we have to plug in some values in each one of these 3 pieces and see if the result is positive or negative. So plug in negative 4. We plug in negative 4. We have negative 4 minus 4 over negative 4 plus 3, right? So, I mean, that's negative, right? It doesn't really matter what it equals. What matters is if it's negative or not. What is this? Negative 8 over negative 1. Oh, excuse me, that is positive. But yeah, the value does not matter. What matters is if it's positive or negative. So this was a double negative but positive result. So we're positive here. Plug in numbers to the left of negative 3, the result will be positive. Okay, here we could plug in 0, it's probably the easiest. If we plug in 0, you do 0 minus 4, 0 plus 3. So negative 4 over 3 is negative. So in here, the outputs will be negative. Okay, let's plug in the number 5. 5 minus 4 over 5 plus 3, right? So 1 over 8, positive. These will give us positive outputs. Okay, so we were looking for greater than or equal to 0. So the solution will be negative infinity to 3 or 4 to infinity. Okay, so you may be asking yourselves, why did we have to test this value? Because when we were dealing with polynomials, we only had to test numbers to the left and right of the zeros. But the thing with rational equations is so here we had a 4, -3. So we're not allowed to plug in -3. So what that does to the graph is it kind of shoots it up, or it could shoot it down. In this case, the graph will look, the graph probably looks like this. Is it equal to 0? I don't know, maybe that's just a really rough sketch of this graph. But the point is, if you're not allowed to plug in a -3 in this case, what it does to the graph is something like this. It either shoots up or it shoots down. So even though it doesn't cross the x-axis, it could still change from positive outputs to negative outputs on the value where the bottom would be 0. So to summarize how we solved this rational inequality, we first found the value that made the top 0, the value that made the bottom 0. We put them on a number line, and then we tested points to the left and right of those. We found that the outputs are positive in here, outputs are positive in here, and in this particular problem we wanted positive outputs, so this was our solution. Okay. Now let's look at another example. Okay, I don't know, x squared minus 1 over 3x plus 1 less than 0. Okay, so here we find when the top is 0, the top will be 0 at plus or minus 1. The bottom will be 0 when plug in negative 1/3. We're going to have to test these numbers. We'll have -1, -1/3, and +1. So now we broke the number line into 4 pieces. And we're going to have to test a number in each one of these 4 pieces. Okay, so I'll begin here. We could plug in -2. Plug in -2. We have -2 squared minus 1 for 3 times -2 plus 1. So that's 4 minus 1 over -6 plus 1, 3 over -5 negative. So in here, the outputs will be negative. Okay, now let's plug in a number here. So 0 is about there, so we want one. I don't know, should we do -2/3? -2/3 will work. If we test -2/3, -2/3 squared minus 1 over 3 is -2/3 plus 1. Okay, so that's 4 over 9 minus 1 divided by -2 plus 1. Right, these 3's cancel. So that's 4 minus 9 all over 9 all over -1. I skipped a few steps there. Let me do that a little slower. So let me take this, come down here with it. We have 4 over 9 minus 1, but I'll call 1 9 over 9. The whole thing is -2 plus 1, which is -1. Right, so that's -5 over 9, -1. So double negative, we end up being positive. And it doesn't really matter what the number equals, so I'll just leave it like that, because who cares? All right, this is positive. Okay, let's see, what were the points here? 1/3. So we could test the number 0. It's an easy one. If we test 0, we do 0 squared minus 1 over 3 times 0 plus 1. So you get negative 1 over 1 is negative. So sorry that I wrote that in green, but here we get negative outputs. Okay, last thing to test, say the number 2 will work. We do 2 squared minus 1 over 3 times 2 plus 1. That's 4 minus 1 over 6 plus 1, positive. Okay, now what do we want? We want the output to be negative. So that happened here, and it happened here. And therefore the solution to the problem, negative infinity to negative 1, or negative 1/3 to 1. And I used open parentheses here because it was a strict inequality, right? We did not have the equality symbol. Okay, so sort of the same method to do rational inequalities. It's just we have that added condition where we test when the bottom is 0 as well. Let me maybe do one more example that's a little more difficult. So let's look at 3 over x plus 1 minus 2 over x minus 1 less than 0. Okay, so here we're minusing fractions. We need a common denominator. So I'll multiply an x minus 1 to the top and bottom of the first term. I'll multiply an x plus 1 to the top and bottom of the second term. And then we have the following. 3x minus 3 minus 2x minus 2 all over x plus 1, x minus 1 less than 0. Okay, so 3x minus 2x is x, negative 3 minus 2, negative 5. Okay, so now we've cleaned it up. Now we take note of when the top is 0, that's when x is 5. And the numbers we're not allowed to plug in that are on the bottom. We cannot plug in a 1 or negative 1. Okay, so we'll cut the number line into 4 pieces. We'll have to test this piece, test a number in here, test a number in here, and test a number there. So if we plug in negative 2, we have negative 2 minus 5 over negative 2 plus 1, negative 2 minus 1, so negative 7 on top, negative 1, negative 3, so that's a triple negative. Triple negative is still negative, and therefore numbers on this piece of the x-axis will give us negative outputs. Okay, let's test the number 0. It's an easy number. If we plugged in 0 to the problem up above, we would have the following. A double negative, which is positive. Okay, plug in 2. If we plug in 2, 2 minus 5, 2 plus 1 is 3, 2 minus 1. Okay, so negative 3 over 3, negative. Negative results in here. Okay, plug in the number 6. We got 6 minus 5, or 6 plus 1, 6 minus 1. Okay, positive, right? No need to even crunch the numbers, because who cares? Positive. Okay, but the problem was asking when is this negative? So we have that as those intervals there are the solution, not. The solution is negative infinity to negative 1 or 1 to 5. Okay, so that concludes today's lesson. Thank you.